Now I want to talk about another one, which has to do with liquids trying to break apart. And so if I look at this, this is a picture of a water drop hanging from a platform up above. And it's in the process of trying to separate. The liquid on here is going to fall off from the liquid up above. And so what's remarkable about this? Well, this is still connected here, but just a slight instant later, this will be disconnected, and we know that that's a real change. The topology of this thing has changed. It was once singly connected, and now it's two separate pieces of liquid. Okay, so what else do we know about this transition? This a topology change. But also, if we look just at this region here, that neck has shrunk to zero at that point. That is, up above it's some finite amount, but in order for this thing really to separate, that neck has to really shrink more and more and more until it actually goes to zero. If it didn't go to zero, it would still be connected and I wouldn't have the transition. So if this thing breaks apart, this radius here has to shrink to zero. And if it shrinks to zero, then one thing we know about using surface tension again is that the surface tension times the curvature, which is now 1 over this radius, so it's infinite, that's the pressure difference between the inside and the outside of this fluid. So that's just a fact of fluid mechanics. And so what this is saying is on the way to this transition, we're getting an enormous change. That is, the forcing has suddenly gone infinite just at that point where this neck is going to zero. And so we have infinite forcing at this point. And so how do we begin to understand this problem? And so, you know, there are computers all over the world trying to simulate this. And so you simulate it on one scale. And so you want to get closer to the singularity, so you get closer. And so you work harder, and you have to get more points in that little region where it's getting closer. You still have to resolve this thing, and you work harder, and you got a little closer. And but that's not good enough, so you go a little harder, and you get a little closer. Work harder, get a little closer. And Zeno's paradox all over again. No matter how hard you work, you don't get to the singularity. You can only approach it. You don't get to the other side. And so computers are all struggling to do this. And then you look out the window, and you see a drop hanging there, and it just drops. And, you know, nature is not trying to think, well, what do I do now, and should I compute something? It just does it. And so the fact that we go through all these conniptions to try to understand this means that there's something we didn't understand about how this drop breaks apart. That is, if we did understand it, we wouldn't have to, we could do what nature does, but not understanding this, we're stuck on one side of the singularity. And so that was what we were trying to figure out, is how do we understand this breakup event in this case. And so is this relegated just to drops? And so again, I want to point out that there's connections to other areas of physics. And so here this is maybe the most famous image taken by the Hubble Space Telescope. This is the star-forming region of the Eagle Nebula. And what's going to happen here? These kind of cylinder-type things are going to break up into stars. And as that happens, the gas around, these are big gas clouds, and the gas has to shrink in the regions between where this stuff exists. And so as that shrinks away, we have something that looks very similar to the behavior that I just showed you for ordinary water drop falling from a faucet. So this is happening on the celestial scale. We saw what happens at the ordinary scale, and then you go down to the microscopic scale. You can see this in bacterial growth and see how bacteria communicate with each other and get similar things. But then you can even go down to the nuclear scale, and there at the nuclear scale, you know it's a smaller number of particles, but the same type of thing happens. That this is kind of like a liquid drop, and when that liquid drop breaks apart, that's fission, and fission is again an example of drop snap-off. And so you see this on all these different scales, from the celestial to the nuclear scale. And so, you know, it's not something that is just relegated to the experiments about water. And so this is what we wanted to start studying about. And so I should tell you just the first part of this is, so is this liquid going to be unstable to anything? And so the idea is, suppose I took a cylinder of liquid, and I ask, is that stable? And well, you already know the answer because I just told you that is surface tension is going to try and make it into a ball, right? But I'm not going to let that happen. I'm going to try and hold the liquid at this distance and have that cylinder, and with the sides, the ends held at that distance apart, I want to ask, is this cylinder now stable? And there's a simple calculation that you can do, which is just ask, well, how much area does it have? Because the more surface area it has is more expensive for the sand, so it's going to try to shrink the surface area if at all possible. And so you just compare the surface area of a cylinder to a cylinder that has a slight waist to it, so it's a little thicker at the top and the bottom and a little thinner in the middle, and you have to keep the volume fixed throughout because the liquid has to stay there. I can't get rid of the liquid, but I'm just changing its position slightly. And if you do this, you can find out by simple calculus that the surface area actually decreases if the length of this cylinder is greater than the original circumference. And so if that happens, if the cylinder is long enough, this thing starts to go unstable, it goes into this shape, and then the curvature in the middle is even larger, so there's more force there, and it feeds on itself, and it runs away, and this thing really starts to break apart. So this is one of the classic instabilities in fluid mechanics called the Rayleigh plateau instability, and you're familiar with this. You can see this. And so what I'll ask you to do is to take your fingers and stick it in your mouth and get some spit on it. And look. Okay, so you're all a little shy. So what I'm going to ask you to do is tonight when you go home and no one's looking, go to the bathroom. And put a little bit of spit between your fingers, and you'll see a little column. And if you look at it carefully, you will see that this column has this, this starts to ball up into a little sphere in the middle of this thread. And so, because I was pretty sure you'd be too shy to do this, but I don't know why. I can do this in front of you, but you don't do it. No one's watching, but I want to have a picture so you could see what you would have seen. And so this is what you would have seen. So this is a spider. This is a bolus spider, so it's not the ones that make webs, but it's a different kind of spider. And so what this spider does is it extrudes this liquid into this drop here, and there's this long thread of gunk that goes from here to its leg. And what you're supposed to look at is, looking along this thread, you see this blobbiness. That's this cylinder breaking up many, many times into, because of this Rayleigh plateau instability that I just told you about, that's what's happening here, that it's getting many different balls as this thing has separated many, many different times. Okay, and so this is my excuse to show you about the bolus spider, but it also shows you something about that you've seen this kind of thing before. Every time you go out in, springtime in Chicago, at least springtime in Chicago, you have spider webs out there, and after a nice cool night and you have dew everywhere, you see that the spider web in the morning is decorated with these beautiful little drops of liquid. That's just the same thing happening, but in a more conventional thing that you know about. Okay, so this is how this instability starts, and then it ends at some point. And so what we're interested in is, how does this instability end? And so what I have here is two pictures of just the end point, as close as we could get to where the drop was breaking apart. And these two things look nearly identical. It's hard to tell apart. And I'm showing you two of them to show you how close they look to one another. But I didn't show you the rest of the drop. And so now I want to show you what I hid from this so you can see what it was that was where these came from. And so these are the two drops that they came from. And so I just uncovered what I had in before. And so you can see this is this region here, and this was that region there. So it's the same thing. It looks the same, but they look very different because what I did with this photograph was I turned it upside down. And so if I turned it upside up so that it was the right way of looking at it, the way it really would have appeared in the movie, what you see is that I get the same behavior down here, point with the cone pointing into the sphere, which is the cone is pointing in the direction of gravity. In this case, I get the cone pointing up into a sphere, and this time it's pointing in the opposite direction of gravity. So there's something here that didn't depend on the forcing that actually got this thing to go in the first place. It was gravity that pulled this thing down, and somehow this thing managed to do the same thing. And so there's something about these drop breaking apart which is universal. That is, it didn't matter about the details of what I was doing. That is, there was something universal about how the drop broke apart. And so that's what I want to emphasize here. And so what I want to show you now is a movie of this drop breaking apart. And I should just tell you just a little bit about how this movie was made. I mean, this was made in our lab in Chicago, which is a very old and decrepit lab, and it's so old and decrepit that the drop is actually going to go sideways. Okay, so gravity was pointing sideways. And so, of course, what we did was we turned the camera on its side so that we had the long aspect ratio. But that's what you're going to see the drop start here and move across the screen, and that is really the direction of gravity. The other thing is that this was taken around 10,000 frames a second and played back at 30 frames a second, so it's a few hundred times slower than what would really happen in real life. And so this is what happens. And so from here to here is about 1.5 centimeters. It's being pulled down. You will see the cone pointing to a sphere in a little bit, right around there. Okay, so I want to show you this because, I've been at pains to try and tell you why these are important scientific problems. But if you ask why am I really doing it, it's because I also think they're beautiful problems. And that this, if you were really honest with you, this is why I come to the lab every day, not because Zeno's paradox. So this is the thing, and I'm not supposed to say that, so don't tell my NSF people, but that's really what drives me in this, and I'm not ashamed of it, so that's why I'm telling you here. Okay, so that's how the water drop breaks apart, but every unhappy drop is unhappy in its own way. And so these are different drops. So this is what you've seen already, which is water falling in air, and you saw the cone pointing into the sphere. This is basically just a more viscous form of water that we took what's called glycerol and mix it with some water. So glycerol you're familiar with because you can buy it at the grocery store or the drugstore, and you can either use it for making cosmetic things, but also to make stronger soap bubbles for your kids if you want to make big soap bubbles. And you probably have a little bit more intimate knowledge of this because I've been told that McDonald's puts it in their shakes to give it that je ne sais quoi de McDonald's. They call it body, we call it viscosity, but it's the same thing. So this is a more viscous form of water falling in air, and you see the shape is very different. That is, it's a long, long cylinder, and then it goes unstable and forms a thin thread. And if we had taken another picture just slightly later, you would have seen this thread go unstable and form an even finer thread. So there's a recurrent thing going on there. This is the pure glycerol on the inside here falling inside another liquid. And so it's an oil, and so they're immiscible with each other. It will still fall if one is heavier than the other, and it will still break apart. And this is another kind of instability. This is a cone pointing into a cone. And this one, I don't know if you can see in the back row, but in the front row, maybe you can see that this is still connected by the thinnest of threads here. And why nature decides that's the way to break up, drop apart is, I mean, I find fascinating that it goes to this length to do such a thing. And so we get, as an experimentalist, to choose which regime we're in because we can vary certain parameters. So what parameters do we get to vary? We get to vary the viscosity of the inner fluid, viscosity of the outer fluid, the density of the inner and the outer fluids, and the surface tension that I keep telling you about, and then this nozzle diameter. And after I've done that, these are basically all the parameters for simple fluids that I get to change as an experimentalist, and I get to tune which regime I want to study in here. And so what I want to now go on is talk about, well, how should we think about this drop breaking apart? And so this is one idea which is, I hope I can get this one idea across. And so it's a little bit, it's not a trivial idea at all. So it's this idea of using scale invariance to try and understand something about that singularity. So what I kept telling you before was that the breakup, when the drop breaks up, the radius is smaller than any other length in the problem. And I kept emphasizing that over and over again. It's not smaller than the molecules, I don't mean that, but smaller than any of the other length scales, such as the drop radius, the length scale on which gravity matters, the length scale on which viscosity matters. These are the various scales that you could define. And because this drop neck is going to zero, it's going to eventually get smaller than any one of those other scales. So it's infinitely smaller than any of those other scales at some point. And the idea is that the dynamics can only depend on the thickness of that thread at that point, that smallest point, and not on any of the other length scales. And so I say that in, not okay, he knows, but why do we say something like that? And so what I want to give you some feeling for this is that if you think about rain coming down on a mountainside, and so the rain comes down everywhere, and it flows into these mighty rivers, and these rivers cross the continent, and then they get to the Gulf, and in the Gulf, this river breaks up into smaller rivers, brooks, rivulets, and finally the water flows between two little pebbles in the stream. And what I want to ask you now is, does the flow between those two little pebbles in the stream depend on the fact that the water originally came from a mountainside? No, it doesn't make sense, right? It's forgotten all of that information. It can't keep that information because that was so long ago, that stuff has been erased because it's on a different scale than the scale at which the real thing matters. And so that's the same idea here. That is, the neck is the smallest thing in here, and the flow in that neck doesn't care about those other length scales because they're irrelevant at this point. And so the flow only depends on that shrinking radius, but that shrinking radius depends on the flow, which depends on the radius, which depends on the flow, which depends on the radius, which depends on the flow, radius, flow, radius, flow, radius, flow, radius. And so what I've done here is I've created a fractal sentence. That is, I blow up any part of the sentence and I get the original sentence back. And so this should remind you of one of those things I showed you earlier, the trees, for example, where I blow up on one scale and I get the entire tree back, at least statistically. And so that's the idea here, that this is what gives rise to this self-similar structure. You blow up any part in this system and you regain the original form back that they were talking about. And so this is what gives rise to these universal shapes. And so our job as experimentalists was to try and go and see if this worked. And so what I want to show you here is what the mathematics of that picture that I just showed you was. And it's this particular form. What it's saying is that there are two length scales at this point. One is this scale and the other is this scale. And what I get to do is, if I know what the shape is at one point, if I want it at a later time, I just multiply this scale by something, I get it smaller, and I multiply this scale by perhaps something else. And I just do that over and over and over again, and I can get as small as I want. And so this is a data And I don't want to go into what this data is, but the reason I'm doing this in a public lecture is because you should realize that what we do is not just taking pretty pictures, but that, this is painstaking data to get each one of these points to really be able to understand what that's doing. And so there is real data behind all of the pictures that I'm telling you, and this is just a placeholder for all of the data that I'm not showing you tonight. Okay? And so again, this emphasizes what is universal. And now you ask, well, is this picture truly the case? And then ask about, well, what happens if I did the opposite of what I just did? So before, remember, we were talking about water falling in air. Suppose I did the opposite of that, which is air rising in water, otherwise known as an air bubble rising. And so this is the work that was done by Nathan Kime, who is back there. And so he did this when he was with us. And so what I want to show you is a very careful experiment that he did. This was a very circular nozzle, very carefully leveled. So this is as level as he could make it. And now we will see how this thing starts to rise. And so it's rising. Get the same kind of thing. And you can see a little drop went up at the top and comes down. It's, again, a beautiful set of a beautiful movie here. But what was bizarre about what I just said was that I went to great pains to tell you that Nathan did a very careful experiment, and it was very circular and very balanced. I didn't tell you that about any of the other experiments. I mean, I just said this is the way it was. So why did I tell you that about this case? And the reason I told you that about this case is that there's something fundamentally different here than in that other case. And I can show this to you in the most blatant movie that I've seen, which is just focusing on that region in the middle. And we will see this happening. And now we've done something to make this as non-circular as possible. It's a slot nozzle. And we blow Nathan had the air come out rather quickly at this point. And now we will see what this looks like. And you'll see that shape. It doesn't look like that simple thing that I've been showing you all along. Something very different is here. There's structure on all these different scales. So let's go back and see this once more. Let's see if I can. Okay, so if I go here, for example. I mean, so this is this neck breaking apart. This is not that smooth variation that I've shown you in all the other ones. This looks like the liquid was torn. And, like a sheet of paper tearing from this thing from one side and the other side. You get these different pieces coming in. And I remind you that there's nothing less likely to tear than air and water. And that's all that's going on here. And so something very different is happening